Matthias Brendel. He is our keynote speaker, and he will discuss the challenges faced in e-vehicle development. Matthias is Vice President at AVL for the business field Electrification. Matthias studied mechanical engineering at the Technical University in Darmstadt in Germany, and he started his career at GM in Europe, at Opel in Rüsselsheim in 1995, not quite 1984, so you're younger than me. He also held several positions in the area of fuel cell development, battery systems and electrical systems, and safety and interior. And he has held the position of Vice President at AVL since 2017. Matthias, are you there?
Yes.
That's good news. The floor is yours.
So good morning, everybody. I'm glad that I have the chance here to talk to you all in that interesting subject there. I'm trying to draw here in the presentation the bigger picture and the challenges of battery electric vehicles. I'm sure that a lot of you are a long time part of that electrification business. Like Andrew was saying, I was a long time, so 20 years ago actually, already working on fuel cell electric vehicles. And always these topics, even if you work on a detail, on an expert level, you always need to put things into perspective. So infrastructure questions, where is the energy actually coming from? How do you compete with efficiency with other technologies, and so on and so forth. And I'm trying to draw a bigger picture and put things into perspective. So what I'm going to talk about is where's the energy actually coming from? So renewable energy is key, that this is accelerating and also supports then the entire energy, the entire change also in mobility. How does the carbon footprint of the battery electric vehicles or the rest of the vehicles also look like, and how to deal with that, and what could be the improvements? And then I have a section of market and some technology trends where I would like to conclude. So looking into the energy discussion, and probably a lot of you know that there's also a big push for hydrogen right now. In Germany, there's a lot of funding for hydrogen. Overall in Europe, there's a big push for hydrogen, also in other regions. And this is all also in the context of renewable energy and in the entire energy sector. And when you look into how much energy actually is available there for renewable energy, it's a lot. And it would be way more than you actually need for the world energy consumption. So the potential is really there. So the question is more, how can you really get hold of all of that energy? How can you store that energy? And how can you make that energy available also in a lot of regions in the world? And even here in Europe, we're fighting with a lot of the infrastructure for electrification. But when you think about other regions that are more emerging markets like India also, that have a basic problem with electricity grid, and you don't reach all regions, you can think about the problem with a worldwide perspective is significant and really difficult to resolve. So looking into the energy mix today, you can see that a lot, it's big differences on the one hand, and on the other hand, there is also still a big portion of the energy provided by fossil energy carriers. And but the outlook does not look so bad. So when you look at 2040, there is a big change that much more regenerative energy will be provided. So there's a lot of commitment. There's all the commitments to the Paris Climate Agreement. And so the outlook actually looks there pretty promising, but there's a way to go. And when you listen to the discussions in the energy sector, they also complain a lot about these high challenges and the speed that they need to do, and that the plans that they have really in place might not be sufficient to fulfill all these needs and requirements. Okay, what does it mean then for the vehicles and for reviewing the vehicles? So there you also need to differentiate when you have really a good and sufficient source of renewable energy. There are different pathways. So for sure, it would be kind of very likely that the battery electric vehicles are directly charged by green energy, but you also need to see how do you store the energy in between, how do you transport the energy, where is the renewable energy actually coming from? So where is the source? Is it close by? Is it very remote? There's a lot of talk about using also maybe North Africa for using solar energy there and somehow transmit it then to other regions. But you also can see that there is a lot of discussion about e-fuels and power to gas or power to liquid bigger plants that transform then regenerative energy for combustion engines. So also other pathways, and I mentioned already fuel cells, and for sure with electrolyzers you can also transform the energy, the electrical energy into hydrogen and use then the hydrogen directly for fuel cell, or maybe as an intermediate storage and transform it then later on to maybe e-fuels, or maybe back again into battery electric. So a lot of pathways to consider, all make sense, all have their applications, and I think this is always very important to stay there open, also in respect to the applications and also to the different technologies. So thinking about the carbon footprint, so a lot of discussions there about also thinking about the entire process of a vehicle and its components. So where is actually the base material, the raw material coming from? How much energy and what pathways do you have within manufacturing? Then the actual use of the car. So where is the energy for the daily use coming from? How does the infrastructure look like? And then also in the end of the life of a vehicle, how do you recycle? Can you do a lot of reuse of the recycling? Do you put maybe the battery, for instance, into a second life, into a second usage? So a very broad and very complex picture. And when you think about, I'm sure that you're also involved in those discussions, a lot of the industry is kind of unhappy and complaining about the current regulation that their tank to wheel is mostly addressed, and it does not consider the full picture. So when you think about the CO2 footprint, it's just one slice of the entire chain. And so it's very, very difficult to go through all these sectors, then also with regulations, to have a fair approach that in the end really helps the overriding goal with climate change and Paris climate agreements. So taking a look at the earlier steps there in the process, so in the production. So how does that actually look like in a comparison? So you can see that from a conventional vehicle with 36 tons of CO2 compared to a hybrid electric vehicle, battery electric vehicle, or fuel cell electric vehicle, I think what is significant to monitor is that the share there of what energy and what CO2 emission goes into lifetime, so or in the operation of the car, and what element there goes in the production. And you see that this the share there is changing there from a combustion engine vehicle to a battery electric, or also different on a fuel cell electric vehicle. And as we are focusing today on battery, I'm taking out here the battery part there, where you can see that a lot of the CO2 emission is coming into the plant in the production phase. And this, I think you all read about those studies, that the vehicle is actually starting then with a baggage of CO2 emission, and to get even with the today's maybe mild hybrid, more or less clean combustion engine car, it takes quite a while until this evens out. Okay, looking one step deeper into the battery pack, so very complex, a lot of steps there in the battery production, from cell manufacturing, cell stacking into modules assembling into housing, with a lot of the other components that are then in the end supporting then the entire battery pack. But you can see that a big share of the CO2 footprint is in the cell manufacturing. So 2/3 of the CO2 emissions are actually coming from the cell production. And also taking this into consideration and thinking, what can you do about this? So what we did there was taking a look at the energy mix here, with what you can see here from the European Union. And so you have basically today's standards with 137 a kilogram CO2 per kilowatt hour battery capacity. And you can see with the dark blue, this is the manufacturing part that you need for energy that you use there. And the light blue is the material that you use from how you exploit the material and transport and everything. So you have two ways of influencing that. You have on the one hand, the chance to improve your process, which moves that picture from the left to the right. So project improvements with electrode thickness optimization, so less effort, less energy that you need to drying that, maybe less solvent. So there's optimization that you can use there. But on the other hand, for sure, when you change your energy mix, which is also happening there in parallel, you can move the picture from the upper portion to the lower portion. So you have a lot of potential to gain there, which is important that this is used. So I think on the one hand, very important to make sure that the CO2 emission in the beginning of the life of the vehicle and the battery are reduced, but also even if the energy becomes cleaner in the future, I think it's also extremely important that that it is ensured that that we take very responsible care of an efficient use of the energy that is out there. So thinking about the end of life of the vehicle, so more into looking into the recycling. So what we did there was that we compared the three ways to make an assessment how meaningful is it that we recycle in the end a battery and a vehicle. So we looked into into hydrometallurgy, pyrometallurgy, and direct recovery. And direct recovery with a lot of material recovery, very efficient usage, but still in early stages, so still work to do that this really becomes a viable process. Pyrometallurgy, also an economical use. You're not gaining all material out there, but you have a very economical way of doing that. And then the hydrometallurgy, where you have a lot of chemical processes behind there. You have a very high recovery rate of the materials, but it's very costly and energy intense. And when you compare that then in an overall picture, what would that actually mean? On the left side, there's a comparison of lithium and cobalt there from a CO2 footprint. So the orange bar means that is the material they actually get from the source. So it's not a recycled material, that's the original material that you exploit. And the other two bars are showing then the pyro or the hydrometallurgy. So you can see that on lithium, there is no recycling possible with pyro, therefore there is no bar. But when you compare the level of the bars, and this is the message here of the chart, the CO2 emissions are in a similar range. So this could be kind of seen as being kind of neutral. So it makes sense to do the recycling there. And when you go to the right side of the chart, you see there the graph that shows kind of with this kind of lower left to upper right, that is in principle your break-even line. So lithium doesn't make sense. Lithium overall economically makes no sense there to recover, but copper or cobalt, or also when you talk about fuel cells and so on, platinum, that makes sense, is economically feasible, CO2 neutral, you see on the left chart, so that makes quite a lot of sense. And down there you see the recycling rate. So copper in the overall industry, there's a lot of recycling be done in the industry overall. Cobalt maybe to 1/3, but the recovery in the process comes back to very high value. So there's a lot of recovery in the recycling process possible for these materials. So maybe to conclude that section here, there are a lot of questions when you think about that first life of the battery, the second life of the battery, and then the end of the life of the battery that needs to be addressed and answered. So also from kind of the design, where I showed you also from the process, it's influencing what is the operating strategy, the safety of the battery, is a reuse meaningful, when does it qualify for a reuse, how can you predict? So a lot of things where I'm also sure that from going into a better understanding into modeling of the battery and making good assessments with state of health is essential to make sure that there is a good monitoring during lifetime, maybe a good specification in the beginning, and then also a good assessment if a second life or a recycling pathway would be the best steps in doing the most efficient and economically the most meaningful next step then for the battery. And this pictorially just shows you again what I said in words. So all of that is connected to each other. So looking into the processes isolated is not right. You need to take a look into that entire system. And from the beginning on how you exploit the material all the way down to the recycling, there's a logical connection that needs to be considered. And therefore, even if work is done on some detailed level, which is complex and difficult, always important to also maybe change perspective and make sure you connect a lot of dots here. Okay, taking a look now more to the technology itself and also how are the markets right now responding and working. So I put a couple of slides together with market and technology trends that I'm seeing. So right now, taking a look at the current fleet, still highly dominated there with combustion engine, but you definitely see that there is a steep growing curve for electric or electrification. So with hybrids, plug-in hybrids or battery electric, don't see much here of fuel cells. And now we have the situation that comparing the global vehicle sales, and sure you all are to some sort suffering under the current difficult economical situation in your personal life with the COVID situation, and also in your business life with all budgets are somehow under pressure. And you can also see that the market did suffer quite a bit, but there's also signs for recovery. So it looks like that it is stabilizing to some extent again. And when you look into the mix of how does this curve then also looks into the technologies, you can see, well, a combustion engine is recovering, hybrids recovering pretty well, and you don't see, because of my picture down there, the battery electric are not recovering that much. And I think this is an overlay of different effects. It's on the one hand, the economical situation, the crisis, but there are also some incentive schemes did change there in several countries. So the support of battery electric, not everywhere the same. Very strong right now in Europe, very strong in Germany, but other countries did not put those attractive packages out there right now. So this is definitely an element to boost these sales here again. Taking a look at the outlook there, so with quite some bandwidth, but you can see that in 2030, so 10 years from now, there will be a much bigger share. And we compared different sources and compared that also with our internal estimations. So my kind of rule of thumb is that in 2030 we will have a third mix, that we have combustion engine like third, we will have battery full electric vehicles like a third, and then there will be a hybridization there with a mix of in between mild hybrid and strong hybrids, then also about 1/3. And for sure, also to be considered, and therefore also that energy chain, the renewable energy, maybe e-fuels as a transition technology, or maybe for some applications also with a sustainable technology, as a sustainable technology, I think is important that this plays a significant role for some time. And also looking into infrastructure, when you have the electric vehicle discussion, you always talk about infrastructure. With fuel cell, it's not different, it's the same. But you can see that the number of stations is growing fast, the number of charging points is growing fast, also the fast charging elements, so higher than 25, 22, 20 something, let's say, or all the way up to very high power is growing fast. Maybe not needed for everybody, so who can do in his daily pattern home charging, maybe that is the most efficient, most convenient way. It will be slow charging, but this might be when you can charge at home, when you can charge at work maybe. that's for your daily use just sufficient. But when you don't have the opportunity or you are traveling longer distances, then the fast charging is an important way of doing that. And there's a lot of going on still in harmonization of standards, and if it's just the mechanical design of the plug, or if it's communication and paying methods, I think there's still ways to go. That this is very easy, simple, and convenient, and nobody has any hesitations to use an electric vehicle because of those hurdles. And now taking a look here into what's actually going on at the OEM. So you can see the different streams, and there is no wrong and right in my perspective. You have some companies that really where we have companies like that are only working on one technology, so for them the question is not there. But then you have companies with a lot of tradition, with a lot of legacy in their product. So like VW right now is deciding with the ID.3 and also with other products that are upcoming, they go to dedicated vehicle platforms, so dedicated vehicle architectures. And for instance, BMW, even they had with the ID.3 a dedicated electric vehicle out there, they deciding right now to go to a multi-propulsion platform and see the most benefits for them in a combination like this. So you can see both trends. And I think it depends on what economy of scale you have in mind, that the investment of a dedicated platform makes sense. From an optimization perspective, definitely the dedicated platform is something that has more potential. Looking into the value chain, so the whole industry is there in a change and is working on their future plans. And you can see that, for instance, OEMs like VW, but also others, are looking very deeply into the value chain and how deep they do their vertical integration. And for them, it's important that when things like they had in their value chain before, like the combustion engine might not have the long and sustainable future, that this is replaced by something else. So this is the question that they all have to answer. What do I pull inside? Also, there is a lot of discussion about, do I need to do my own battery cell, or do I need to have own capabilities to at least understand the battery cell very clearly, that I can work meaningful with the cell suppliers, and I can also discuss with them on the right technical level. There is a lot going on right now at every OEM. Also from working together or the integration level. So when you see here on the left side, you see systems where you talk like 3-in-1 or 5-in-1, where you integrate more systems into the e-drive. So e-drive then stands for a synonym out of the e-machine, the transmission, and then also for the inverter. Could also include the DC-DC step-up converter, or can also be integrate then the onboard charger. So a lot of integration work going on, and there you always need to find the balance. If economy of scale for the components already justifies that you do an integrated solution, because that does probably then not fit into a lot of applications, because then they need to be customized again. But that really depends on your models. You see e-axles. So e-axles also together with chassis components, like you see here in the middle picture. So there the supply base is trying to merge their capabilities together, very high integration level, very much customized, but also a big part of the value chain. And then on the right picture, that's again the VW sketch there. But what the trend that you see here is actually that the OEMs are trying also to partner or to bring their components or their systems to the market, and to make sure that they have economy of scale, and maybe that they also share the development costs to some extent with other partnerships. And so you see that there are a couple of areas where you can see that competition for the tier one, but on the other hand, probably also a way of ensuring that the technology now is getting bigger volumes and bigger scale. So looking into technology trend here from the e-axle, here I brought one example there. So you can see that there and that there is also a solution that I'm showing here with high integration level. You see 2 electric motors, an integrated inverter, and an integrated transmission, and you're always shooting for very high efficiency, that your thermal efficiency is going up, you minimize the cooling effort, the power density is improved, that you save weight and also space. So there is a lot of trends in going to higher speed, to higher RPMs of the e-machines, like 30,000 RPM. And then also brings also challenges and requirements for very good lubrication and sealing requirements and VH requirements. There's a big trend for the next generation of the semiconductors, and also some features that with kind of a dual e-machine concept like you have here with torque vectoring, and in the transmission there is also the debate of single or multi-speed designs. And putting that on the timeline, on the upper side you see there the power electronics, also something where a lot in the automotive industry is struggling with, because that has not so much connection to technology that they did before. But here is a lot going on there in the power electronics. And so, as I said earlier, next generation of semiconductors, maybe different housings, going away from the metal housing also to plastic housing, save weight, save volume. So the silicon carbide will help then also to get efficiency, to gain also volume and power density. So right now I think we are in the ballpark with the power electronics of 3 to 4 euro per kilowatt, and the goal is there really to cut that in half in the next couple of years. And down there, looking in the e-drive systems, the EU, as I earlier said, going up to the high speed to the high speed solution, highly integrated, very compact designs, and also the balance in between 1-speed or 2-speed designs, depending on the requirements on the vehicle level. Okay, taking a look at the battery. So also efficiency is key, energy density is key. So also very important that you save the space. Looking into the next generation of cell chemistry, there's a lot to do around solid-state technology that has a lot of potential in energy density, also to some extent in cost, but there's also quite challenges out there still in manufacturing concepts, and also different designs in the modularity. So there's still work to do until this really comes significant into the play. So our estimation is more the second half of the decade. Design for manufacturing still plays a role, always safety, then fast charging, and you see down there some key features that go very closely into the understanding of all the mechanisms that are going on in the cell chemistry that connect then in the end there to your battery management system, to your thermal management, maybe the speed, how you can charge, maybe some predictive mechanisms, how you condition the battery before charging, and how you connect a lot of things there. So these are trends that you see here, and from a bigger perspective, one trend that's right now also imminent out there is going away maybe from the I would say the current module design, more to a cell to pack design, and so having bigger formats of cells, and maybe then just having a stack of cells together that already build the pack, or maybe having at least less modules to come to a different modularity. And we did a little bit of an assessment that you see here on the right, with quite some advantages, but also with some challenges that are still there. So from my perspective, there is still a balance that needs to be found in between kind of volume and volume savings that you do there. You not need a lot of the connections that you need for the modularity design, but on the other hand, it's a bit more difficult to make that fit into multiple applications, and that I think is the balance that needs to be found. if it's possible there also to find a standard size that is then in the end for the cell supplier also a good base to fit into many applications. And that triggers down then also to how do you handle that later on in a repair situation, in a rework situation, and so on and so forth. So way to go, but very interesting trend that needs to be considered. And on the other side, then what I think is right now more the current trend that you see, and we're doing quite a lot there also from our side there. It's actually more the modularity approach that's taking into consideration right now, where you need to have a very agile and easy to adapt a manufacturing process, where it's necessary that you adapt to a lot of applications. I think right now this is still the priority to go, but it's also very important to balance it out between the trends that you see there. So product costs, exchangeability, and the bigger picture needs to be considered there. Okay, looking into a couple of elements that I was talking to, so all these are influencing somehow the battery trends, also the system trends. And what I wanted to say with this slide, actually, a lot of it is done with partnerships, with research partners, or in bigger initiatives like the one that you did work on together there. So we really appreciate these cooperations. I'm also part of the Battery Europe initiative that's going on currently, also with the European Commission. I'm part of the governance board there. So I think this is very important that this community here stays closely together to find the best synergies and work very closely together. Yeah, and to conclude my presentation, I just want to make sure that we see all these potentials and that we see that in a big context. I think we have all a lot of passion in that area and need to make sure that all these areas are moving ahead, and we have the viewpoint of connecting a lot of things together. There's potential and challenges in all these areas, but I think we also have great progress, and the future will be electric. So I think we see that very similar. So thank you very much for your attention.
Matthias, thank you very much. Yeah, thank you for the insights. That was fascinating to see how wide you guys are thinking, from materials procurement, production, in use, right down to the grave. And your appeal for modeling, if I heard that right, the ability to model throughout the whole life cycle of the product, and the middle slide there, this ability to shift things. So for me, it ties up with what Marina was saying. There's an urgent need for new modeling and simulation activities. So I can't wait now for the presentations. Matthias, thank you very much.
Thank you. Thank you.